Imagine a fighter jet so advanced that it could outclimb its rivals at a staggering 50,800 feet per minute, break Mach 2 with ease, and do it all while being more affordable and efficient than its peers. Meet the Northrop F-20 Tigershark, a lightweight marvel born from the legendary F-5 Tiger II, but with upgrades that left even the iconic F-16 in its shadow. From cutting-edge radar systems to a record-breaking thrust-to-weight ratio, this jet wasn't just engineering but innovation redefined. But why, despite its brilliance, did it vanish into obscurity? Let's dive into the incredible story of the F-20 Tigershark. The revolutionary vision behind the F-20 Tigershark. Development of the Northrop F-20 Tigershark began in 1975 as part of a strategic initiative to create an advanced lightweight fighter, initially designated as the F-5GS. This aircraft represented a significant advancement in fighter technology, while maintaining cost-effectiveness as its core principle. The transformation from F-5E to F-20 centered on substantial technological improvements. The most significant change involved replacing the F-5E S-twin J85 engines with a single General Electric F-04 engine, which delivered 60% more thrust. Subsequently, this modification enabled the aircraft to achieve superior performance metrics while reducing maintenance requirements. The F-20's development aligned with the U.S. Department of Defense's FX program, which aimed to create fighters capable of matching Soviet aircraft without incorporating sensitive frontline technologies. Primarily targeting the export market, Northrop invested over $1 billion of private funding in the program. The company's strategy focused on delivering advanced capabilities at reduced operational costs, specifically targeting nations seeking modern air defense solutions. The engineering team established 3 primary objectives, including achieving performance superiority while maintaining cost efficiency, incorporating advanced avionics without compromising reliability, and optimizing maintenance and operational requirements. The design philosophy emphasized practical considerations beyond mere performance metrics. Specifically, Northrop's approach focused on balancing advanced capabilities with operational practicality. The engineering team prioritized reliability and maintainability, recognizing their direct impact on sortie rates and overall combat effectiveness. The F-20's development incorporated significant technological advancements, including an all-new avionics suite centered around the General Electric innovated by F-67 multi-mode radar. Additionally, the cockpit featured modern innovations such as a panoramic canopy, a large head-up display, and 2 monochrome multifunction displays, complemented by a complete hands-on throttle and stick control system. The aircraft's weapons integration capabilities proved extensive, accommodating the entire range of Mark 80 series bombs, A-65 Maverick missiles, and both AIM-9 Sidewinder and AIM-7 Sparrow air-to-air missiles, based on a 150-unit production estimate in 1983. The F-20's unit cost was projected at $70 million, offering a 40–50% reduction in life cycle costs compared to contemporary fighters. Groundbreaking engine integration. At the heart of the Northrop F-20 Tigershark's exceptional performance lay its revolutionary General Electric F-04 engine, marking a significant departure from conventional fighter jet propulsion systems of its era. The F-04 engine represented a quantum leap in fighter jet propulsion technology. This powerplant contained less than half the number of parts found in the F-16's Pratt & Whitney F-100 engine, achieving a mean flight hours between failure rate of 190 hours. In contrast to the F-100's 45 hours, the engine delivered 17,000 pounds of thrust with an afterburner, propelling the F-20 to a maximum speed of Mach 2.0 and enabling a service ceiling of 56,800 feet. The F-04 engine integration required sophisticated thermal management solutions. The engineering team developed an advanced cooling system that maintained optimal operating temperatures across various flight conditions. This system proved particularly effective during high-performance maneuvers, as evidenced by the aircraft's ability to sustain a climb rate of 52,800 feet per minute. The thermal management system was meticulously designed to ensure peak performance and reliability under demanding conditions. It included sophisticated heat dissipation mechanisms to efficiently manage high-temperature zones, ensuring that critical components remained within safe operational limits. The system also featured carefully optimized airflow patterns, strategically directing cool air to areas requiring the most thermal regulation. Integrated cooling channels were seamlessly embedded within the structure, enhancing the system's overall efficiency while maintaining a compact design. Additionally, the structural materials were engineered with enhanced thermal properties, allowing them to withstand and distribute heat more effectively, ensuring durability and long-term operational stability. The F-4 engine installation marked a fundamental shift in the aircraft's power-to-weight characteristics. The single-engine configuration provided 60% more thrust than the combined output of the F-5E S-J85 engines, despite adding only 17% to the airframe weight. This optimization resulted in a combat thrust-to-weight ratio of 1:12, surpassing many contemporary fighters. The enhanced power-to-weight ratio yielded practical benefits in operational scenarios. The F-20 demonstrated remarkable readiness, achieving combat preparation within 1 minute after takeoff. In terms of fuel efficiency, the aircraft consumed 53% less fuel than average frontline designs of the period. The streamlined engine design also contributed to reduced maintenance requirements, with only 15.1 maintenance man-hours per flight hour, compared to the F-16's 33.9 hours. The 404's reliability became evident during the aircraft's testing phase, as demonstrated across approximately 1,500 flights before program termination. The engine's performance characteristics enabled the F-20 to carry up to 8,300 pounds of external armaments and fuel across 5 pylons, though this capacity remained slightly below that of its contemporary competitor, the F-16. Advanced aerodynamic solutions. Aerodynamic excellence defined the Northrop F-20 Tigershark's design philosophy, with modifications that enhanced its combat capabilities across multiple performance parameters. The F-20's wing retained the proven F-5E profile while incorporating strategic improvements. Primarily, the modified leading-edge extensions symbolized as legs achieved a remarkable 12% increase in the wing's maximum lift coefficient, while adding nearly 1.6% to the total wing area. The engineering team focused on optimizing the wing's aerodynamic efficiency through careful refinement of the leg geometry, consequently improving the aircraft's overall performance envelope. To enhance the F-20's handling characteristics, engineers implemented a series of carefully considered modifications that significantly improved its performance. One of the most notable changes was a 30% increase in the size of the horizontal stabilizer, which provided greater stability and control during high-demand maneuvers. Complementing this adjustment was the introduction of an advanced dual-channel fly-by-wire control system, a cutting-edge innovation that replaced traditional mechanical linkages, offering precise and reliable pitch management. These enhancements effectively addressed the pitch response limitations that had been a challenge in the aircraft's earlier design. Furthermore, engineers deliberately destabilized the aircraft's pitch to improve maneuverability, a bold approach that, when combined with modifications to the leading-edge extensions, resulted in substantial performance gains across a variety of flight conditions. The improvements were reflected in the F-20's turn performance metrics, which saw a dramatic boost. The instantaneous turn rate increased by 7%, reaching an impressive 20 degrees per second. Meanwhile, the sustained turn rate at Mach 0, 8 and 15,000 feet reached 11.5 degrees per second, showcasing the aircraft's ability to maintain agility during prolonged engagements. Additionally, the F-20's supersonic turn rates exceeded those of its predecessor, the F-5E, by an astonishing 47%, solidifying its reputation as a remarkably nimble and capable fighter jet. The F-20 excelled in high angle of attack, symbolized as AWA operations, evidently surpassing contemporary fighters. The aircraft demonstrated exceptional slow-speed handling, maintaining controlled flight at just 124 km per hour, while achieving a 35-degree AWA. Essentially, this capability exceeded the F-16's 30-degree AWA limitation. The enhanced aerodynamic package delivered impressive acceleration characteristics. The F-20 could accelerate from Mach 0, 9 to 1, in 29 seconds at 9,150 meters. Moreover, the aircraft demonstrated exceptional climb performance, reaching 12,200 meters in 3 minutes. Advanced materials played a vital role in the F-20's aerodynamic refinement. The aircraft incorporated fiberglass components in areas previously dominated by metal construction. This strategic use of composite materials contributed to weight optimization while maintaining structural integrity, further enhancing the aircraft's performance envelope. Digital revolution in the cockpit. Inside the F-20 Tigershark's cockpit, Northrop engineers crafted a digital command center that redefined fighter aircraft interfaces of its era. The integration of advanced electronics marked a significant leap in combat aircraft technology. The F-20's sensor suite was anchored by the General Electric and divided by AIM-7 multi-mode radar, a sophisticated system that provided advanced air-to-air and air-to-ground capabilities. This radar represented a significant leap in operational flexibility and targeting precision. Complementing the radar was a completely overhauled navigation system, which transitioned from traditional electromechanical components to a modern, all-electronic configuration centered around a rain laser gyroscope. This innovation not only enhanced reliability, but also dramatically reduced the aircraft's power on to takeoff time to just 22 seconds, streamlining mission readiness. The avionics architecture of the F-20 was equally advanced, integrating a range of cutting-edge systems. This included the divided by AIM-7 post-Doppler radar for comprehensive situational awareness. Rather than following conventional designs, Northrop assembled a dedicated team of engineers, human factors specialists, and fighter pilots to create an intuitive cockpit layout. The design featured a wide-angle head-up display with an upfront controller and two high-set, monochrome multifunction displays. Indeed, the cockpit's ergonomic layout prioritized pilot efficiency, incorporating hands-on throttle and stick controls for seamless operation. The weapons management system demonstrated remarkable sophistication. Primarily, the three-position air-to-air weapons selector enabled quick transitions between being visual range weapons, infrared homing missiles, and GUS. The system supported the integration of Mark 80 series bombs, AIM-65 Maverick missiles, and both AIM-9 Sidewinder and AIM-7 Sparrow air-to-air missiles. The F-20's mission systems prioritized reliability and operational efficiency. Triple redundant systems protected critical flight controls, while advanced fire suppression mechanisms enhanced survivability. The digital flight control system, coupled with the mission computer and laser inertial navigation system, provided precise control and positioning data. Foreign pilots mastered the F-20's sophisticated systems after just 2 days of simulator training. This rapid adaptation validated Northrop's focus on intuitive design and operational simplicity. The aircraft's mission-ready status could be achieved at 40,000 feet altitude, significantly enhancing its quick reaction capability. The Production Development Center played a crucial role in perfecting these systems. As the first aircraft developed in this facility, the F-20 benefited from advanced design and development processes. The emphasis on production efficiency and proper tooling configuration ensured consistent system integration across the manufacturing process. Combat capability enhancements. The F-20 Tigershark's combat capabilities positioned it as a formidable fighter aircraft, equipped with an extensive array of weapons and advanced combat features that enhanced its battlefield effectiveness. The F-20's weapons integration system was designed to accommodate a wide variety of armaments, utilizing 9 hardpoints to maximize its combat versatility. The aircraft could be equipped with AIM-7 F-20 Sparrow medium-range missiles for beyond visual range engagements, AIM-9 Sidewinder missiles for short-range combat, and AIM-65 Maverick air-to-surface missiles for precision strikes. It also supported Mach 80 series bombs, 2 75-inch folding fin aerial rockets, and a 30mm Pumitas-5 divided by a gun pod for ground attack missions. For close-in engagements, the F-20 was armed with 2 internal 20mm M39 cannons, further enhancing its multi-role capabilities. While the F-20's low-mounted wing design imposed some constraints on weapons placement, particularly with hardpoint weights limited to 1,000 pounds toward the outer wing sections, the central fuselage mount offered remarkable flexibility. This central mount could carry a single NK-80 for 2,000-pound bomb or up to 5 NK-80 to 500-pound bombs, enabling the aircraft to deliver substantial payloads when required. The F-20's beyond visual range, referred to as BVR for short, combat capabilities surpassed those of contemporary fighters. Primarily, the aircraft gained an advantage through its ability to fire the AIM-7 Sparrow missile, a feature the F-16 lacked until the Block 15 ADF version in 1989. The General Electric and divided by AIM-67 multi-mode radar served as the cornerstone of this capability, offering extensive air-to-air and air-to-ground modes. In terms of BVR engagement, the F-20 demonstrated superior target acquisition and tracking capabilities. The aircraft's combat radius extended beyond 5 kilometers, placing it firmly in the BVR combat category. Ultimately, this capability proved crucial for intercepting and engaging threats before they could close to visual range. For close-range engagements, the F-20's small size made it a challenging target to spot visually. The aircraft's agility and close combat scenarios benefited from its advanced aerodynamic features and powerful engine. Test programs validated these capabilities through extensive weapons firing trials, including successful launches of AIM-9 Sidewinders and comprehensive gun pod evaluations. The F-20 met or exceeded all performance goals set for its combat operations. These achievements encompass crucial metrics such as scramble time, mission-capable status at 40,000 feet altitude, and successful weapons deployment throughout approximately 1,500 test flights. The aircraft consistently demonstrated its combat effectiveness. Maintenance and reliability innovations. Engineering excellence in the F-20 Tigershark extended beyond performance metrics into groundbreaking maintenance and reliability innovations. Northrop's commitment to operational efficiency resulted in an aircraft that required 52% less maintenance manpower and demonstrated 63% lower operating and maintenance costs compared to contemporary fighters. The F-20's maintenance architecture prioritized accessibility and efficiency. Maintenance crews achieved unprecedented service rates, with the aircraft requiring only 15 maintenance man-hours per flight hour, fundamentally outperforming the F-16's 33 9 hours. This dramatic reduction stemmed from strategic design choices that simplified routine maintenance procedures. The F-20's service-oriented design was specifically engineered to support rapid deployment, making it a highly responsive and efficient fighter. One of its standout features was the ability to achieve a power-on-to-takeoff time of just 22 seconds, significantly enhancing mission readiness. This was further supported by streamlined pre-flight checks that reduced preparation time without compromising safety or performance. Additionally, the aircraft's design included optimized access paths that provided quick and easy access to critical components, facilitating efficient maintenance. Integrated diagnostic systems added another layer of efficiency, enabling swift identification and resolution of potential issues to ensure the aircraft remained mission-ready at all times. The F-20's reliability metrics set new standards in military aviation. The General Electric engine achieved a mean flight hours between failure rate of 190 hours, markedly superior to the F-100 engine's 45 hours, throughout approximately 1,500 test flights before program termination. The aircraft consistently exceeded planned reliability targets. Northrop's approach to reliability is centered on selecting proven subsystems or components with superior reliability specifications. This approach delivered outstanding advancements across various systems. The avionics achieved unprecedented levels of reliability, ensuring consistent performance in demanding conditions. Structural durability was significantly improved through the use of composite materials, providing greater resilience and longevity. Service access points were thoughtfully designed to simplify maintenance, reducing complexity and downtime. Additionally, integrated diagnostic capabilities enabled rapid troubleshooting, streamlining repair processes, and maximizing operational efficiency. The F-20's cost-efficiency innovations extended across its entire operational spectrum. Under fixed-price contracts, Northrop offered the aircraft at $15 million per unit, with a spare parts package priced at $8 million per aircraft. This pricing structure promised significant savings, ultimately reducing life cycle costs by approximately $10 million per aircraft over a 20-year service life. The cost reduction strategy incorporated multiple technological innovations. The aircraft's simplified maintenance requirements translated to substantial operational savings, requiring half the manpower needed for the F-16. These efficiencies resulted from several key innovations. Advanced diagnostic systems played a crucial role in reducing troubleshooting time, allowing for quicker identification and resolution of issues. Simplified component access further contributed by making servicing less complex and more efficient. The enhanced reliability of the systems decreased the frequency of replacements, ensuring longer intervals between maintenance. Additionally, streamlined maintenance procedures improved overall operational efficiency, reducing downtime and enhancing the aircraft's readiness. The F-20's reliability optimization extended beyond individual components to encompass the entire system architecture. Foreign pilots demonstrated the aircraft's operational simplicity by achieving qualification after just 2 days of simulator training. This rapid qualification process underscored the success of Northrop's integrated approach to reliability and maintainability. Performance testing and validation. Rigorous testing validated the F-20 Tigershark's exceptional capabilities through an extensive flight test program that spanned multiple years and accumulated approximately 1,500 flights. The United States Air Force oversaw the testing program from its inception, ensuring adherence to stringent military standards. The inaugural flight on August 30, 1982, piloted by Russ Scott, established the aircraft's baseline capabilities. During this 40-minute maiden voyage, the prototype climbed to 40,000 feet and achieved Mach 1.04. Primarily, the first prototype, serial 82-62, demonstrated remarkable reliability, accumulating 240 flights. By April 1983, the second prototype, serial 82-63, took flight on August 26, 1983, featuring a complete avionics suite. Fundamentally, these initial prototypes served as production-quality aircraft, rather than mere test platforms, reflecting Northrop's confidence in their engineering approach. Combat capability testing thoroughly validated the F-20's performance across a wide range of scenarios. The aircraft successfully demonstrated its versatility by launching AIM-9 Sidewinder and AIM-7 Sparrow missiles, deploying AIM-65 Maverick missiles, firing two 75-inch folding-fin aerial rockets, and dropping Mk-82 bombs with precision. Additionally, the 30mm Puminas 5 divided by a gun pod was effectively operated, showcasing the aircraft's adaptability in various combat roles. The F-20's low-speed handling was particularly impressive. It maintained controlled flight at just 124 km per hour while achieving a 35-degree angle of attack, surpassing the F-16's 30-degree limitation. The aircraft also exhibited remarkable acceleration, rapidly reaching Mach 0.9 to 1 in just 29 seconds at an altitude of 9,150 meters, further proving its exceptional combat capabilities. The Air Force's oversight, formalized through a May 1983 Memorandum of Agreement, established their responsibility for certifying the F-20's performance, airworthiness, and fixed-price program parameters. Ultimately, the aircraft met or exceeded all planned performance, reliability, and maintainability objectives across nearly 1,400 sorties. Performance validation covered several crucial aspects to ensure the F-20's readiness and capabilities. Scramble time was optimized, allowing for rapid response in critical situations. The aircraft achieved mission-capable status at an altitude of 40,000 feet, demonstrating its operational range. Both instantaneous and sustained turn rates were evaluated at various altitudes, confirming the aircraft's agility in different flight conditions. Acceleration through multiple airspeed ranges was also assessed, showcasing its versatility in various combat scenarios. Additionally, the performance of the weapons system was tested, including its ability to deploy armaments and acquire targets effectively. The F-20's maintenance efficiency proved superior, requiring 15.1 maintenance man-hours per flight hour compared to the F-16's 33.9. Accordingly, Chuck Yeager, serving as Northrop's spokesperson, endorsed the aircraft as magnificent based on its demonstrated capabilities. Foreign pilot certification demonstrated the F-20's operational accessibility, with pilots achieving qualification after just 2 days of simulator training. The aircraft consistently outperformed contemporary fighters in specific metrics, including scramble time and fuel efficiency. Throughout the testing program, the F-20 exhibited exceptional reliability. The mean flight hours between failures exceeded planned rates. These results validated Northrop's design philosophy, confirming the aircraft's potential as a cost-effective, high-performance fighter platform. Engineering lessons and legacy. The legacy of the Northrop F-20 Tigershark extends far beyond its prototype status, establishing engineering principles that continue to shape modern fighter aircraft design. Aviation author Steve Pace acknowledged the F-20 as one of the best fighters that never went into production. The F-20's engineering philosophy fundamentally altered fighter aircraft development approaches. Primarily, its emphasis on reliability and maintainability established new benchmarks, achieving 63% lower operating costs and requiring 52% less maintenance manpower than contemporary designs. The aircraft's innovative production development center introduced revolutionary manufacturing processes, bringing designers, engineers, and manufacturing supervisors under one roof. The Production Development Center's team-to-based approach yielded remarkable results in production efficiency. Principally, this collaborative environment led to significant improvements in quality control and group cohesion. The emphasis on proper tooling configuration and design optimization became a model for future aircraft development programs. The F-20's technological innovations were successfully applied across various platforms, with the General Electric and divided by AIM-7 radar standing out as the program's most successful component. This radar system was ultimately adopted by several notable programs, including Taiwan's Chingguo fighter program, South Korea's Kai-50 Golden Eagle trainer aircraft, and multiple advanced training platforms. The aircraft's advanced avionics architecture influenced subsequent fighter designs. Hence, its integrated systems approach, combining sophisticated radar capabilities with user-friendly interfaces, established new standards for cockpit design. The success of these transfers validated Northrop's approach to technology development and integration. The F-20's influence persists in contemporary aircraft design. Generally, its emphasis on cost-effective performance and operational efficiency mirrors current lightweight fighter development priorities. The aircraft's maintenance optimization strategies, which achieved a 52% reduction in maintenance manpower requirements, continue to inform modern aircraft sustainment programs. Northrop's innovative approach to production technology, highlighted by the establishment of the Production Development Center concept, set lasting standards for aircraft manufacturing. This approach revolutionized routine production processes by integrating design and manufacturing teams, improving collaboration and efficiency. Enhanced quality control procedures ensured the highest standards of performance and reliability, while streamlined production workflows minimized delays and maximized throughput. Additionally, the use of advanced tooling configurations played a key role in improving precision and reducing production time, further advancing the company's manufacturing capabilities. The program's impact on military procurement practices proved substantial. Thomas McNaughton noted that competition between the F-20 and F-16 generated massive savings for the U.S. government. This competitive dynamic established new parameters for cost-effectiveness in fighter aircraft development. The F-20's technology transfer success demonstrated the value of modular system design. Principally, the N divided by AIM-7 radar's adoption by multiple programs validated Northrop's approach to developing versatile, adaptable systems. Likewise, the aircraft's maintenance innovations influenced subsequent fighter programs' supportability requirements. In terms of operational efficiency, the F-20's achievements in reducing maintenance requirements and improving reliability continue to guide modern aircraft design. The program demonstrated that sophisticated capabilities need not compromise operational simplicity or maintenance efficiency. These lessons remain relevant for contemporary fighter development programs seeking to balance performance with sustainment costs. The F-20's impact on production technology left a lasting legacy, particularly through the introduction of the Production Development Center concept, which transformed aircraft manufacturing. This innovative approach emphasized concurrent engineering practices, allowing design and production to progress simultaneously, enhancing efficiency. Integrated team structures foster collaboration across various departments, improving coordination throughout the manufacturing process. The focus on quality-driven production processes ensured superior results at every stage, while advanced tooling optimization significantly improved precision and minimized production time, setting new standards for the industry. These innovations contributed to broader changes in aerospace manufacturing methodology. Similarly, the program's emphasis on reliability and maintainability established new standards for fighter aircraft development, influencing subsequent programs' design priorities. The F-20's impact on technology transfer practices remains noteworthy. Ultimately, its success in developing transferable technologies, particularly in radar and avionics systems, demonstrated the value of modular design approaches. This legacy continues to influence modern military aircraft development programs, particularly in nations seeking to establish domestic aerospace capabilities. The Northrop F-20 Tigershark is a remarkable example of aerospace engineering, showcasing groundbreaking capabilities despite never entering production. With its advanced F-404 engine, sophisticated aerodynamics, and innovative digital cockpit, the F-20 achieved impressive performance metrics, including Mach 2, 0 speed, and a climb rate of 52,800 feet per minute. Its weapons integration and combat features positioned it as a formidable fighter, while engineering advancements reduced maintenance and operating costs significantly. Although it never saw full production, the F-20's legacy continues through its technological innovations, particularly the undivided by AIM-67 radar, which was later adopted by other aircraft programs. The Production Development Center concept also left a lasting impact on manufacturing practices. What do you think? Could the F-20 have changed the course of military aviation if it had been mass-produced? Share your thoughts in the comments below. Thank you for watching.